Hi, in this video I will introduce you to the datasets used for task 3 of the DCASE Challenge 2018 and give a quick overview of what can be done with them. DCASE stands for Detection and Classification of Acoustic Scenes and Events. The DCASE community runs a yearly challenge called the DCASE Challenge. Task 3 of the DCASE 2018 challenge was to design a system that, given a short audio recording, returns a binary decision for the presence or absence of bird sound. 3 development datasets and 3 evaluation datasets have been provided for the challenge. All files are 10-second long WAV files, except for the Poland NFC dataset, which contains 1-second long clips. All files have been manually labeled with a 0 or 1 for absence or presence of bird sound. The Freefield 1010 and the BirdVox DCASE2018 datasets have been passively collected using controlled equipment. That means that researchers installed recording stations in different locations that constantly record audio. In contrast, the Warbler B10K dataset has been crowdsourced by users of the bird recognition app Warbler, meaning the recordings have been actively captured with uncontrolled equipment. This dataset is also biased towards good weather and daytime. The first evaluation dataset includes additional recordings from the same conditions as the Warbler B10K development dataset. The other 2 evaluation datasets include data more similar to the Freefield and BirdVox datasets, as they have been passively captured using controlled equipment. While the held out part of the Warbler dataset has been recorded under the same recording conditions as the part included in the training data, the other 2 evaluation datasets do not share this characteristic. Consequently, most of the evaluation data has been recorded under entirely unseen conditions. The datasets are all downloadable on the DCASE website and are all in the same format. The audio files are compressed into a zip file, while the labels are available as CSV files. The CSV files look like this. Each row corresponds to one WAV file. There are 3 columns. The item ID column contains the name of the corresponding WAV file. The dataset ID is the dataset the file is in. The has_bird column then shows the annotation itself. 0 means that the file does not contain bird sound, while a 1 means that it does. All sound files were normalized in amplitude and saved as 16-bit mono PCM at 44.1 kHz sampling rate. They are all available under open licenses. Now, let's listen to a few examples so you get an impression of how the recordings sound. At first, let's listen to an easy example from the Freefield dataset. In this example, there's little noise and we can clearly hear the bird song. Let's listen to a more difficult example. In this file, we can barely hear the bird, as another noise is much more dominant. Many files from the BirdVox dataset have a hum, like this one. The Warbler dataset also has bird sound, imitated by humans, like in this example. These files are annotated as not containing bird sound.
That's 2 birds. One going to it, the other one
I don't think.
Now that you have an understanding of what the datasets look like, let us take a look at the statistics. As annotation data has only been made public for the development datasets, The percentage of positives is unknown for the evaluation datasets. This is because the challenge organizers planned on using the evaluation datasets for future challenges. Of the free field datasets, 7,690 files, about 25% are annotated as containing bird sound. For the warbler dataset, that is the case for about 75% of its 6,045 files. The birdvox dataset is the largest one, with a total of 20,000 files. It is very balanced, with almost exactly 50% of the files containing bird sound. That gives us a total of 33,735 files in the development datasets. The evaluation datasets hold a total of 12,620 files. As the labeling was done manually, it had to be checked for reliability. According to the challenge organizers, the inter-rater reliability was measured via the AUC as 96.7%. As the entry's performance was ranked by area under the ROC curve, or AUC for short, I will mention the metrics ROC and AUC multiple times in this video. Explaining in detail how they work exceeds the scope of this video, but there are great explanations available on YouTube. You now know how the datasets are structured, how they were created, and what their statistics are. As mentioned in the intro, we will now explore how the data can be used for machine learning. To do that, we will have a look at some of the top performing challenge entries. This table is an excerpt from the challenge organizer's article about the challenge's results. It is shortened to only show entries reaching over 80% AUC. The winning entry reached an AUC of 88.7%. The table shows that almost all well-performing entries used spectrograms that were then fed to CNNs. That means that the input to the neural networks was not audio, but image files. This method is very common in audio classification, as it can make use of CNNs pre-trained on large image datasets beforehand. But how do these spectrograms look? A spectrogram is a visual representation of an audio signal. The spectrograms used in this application are two-dimensional heat maps. On the x-axis, we see the time. On the y-axis, the frequency is plotted in a logarithmic order. At every time interval, an intensity value is assigned to each frequency, resulting in the spectrogram. Let's have a look at the spectrogram of the first file we listened to earlier. The bird sound reflects in a specific pattern. In simplified terms, these patterns are what the CNN learns to recognize. This way, it is able to give a number between 0 and 1 for every spectrogram stating the confidence. After doing this for all the evaluation files, an ROC curve can be plotted and the AUC can be calculated. This plot shows the ROC curves of the 4 highest scoring entries and the lowest scoring one. Apparently the curves are asymmetrical. They tend to stay close to the left edge, but not to the top edge. This shows that there is a spread in difficulty for the files. Some files are easy to classify as containing bird sound, while many others are more difficult. In their paper, the challenge organizers examined 500 items where predictions from the strongest systems deviated most from the revalidated ground truth. They did this to find the most common errors made by even the best performing machine learning systems in the detection of bird audio. The category clear means that the bird sound was subjectively clearly audible and should have been detected. Don't know means that the reason for the mistake is not obvious, even if the file is not very clear. The table shows that the most common reason for false negative labeling was that the bird noise was faint or short. Noise, insects, and unusual bird sounds also commonly led to false negatives. The most common reasons for false positives were sounds made by insects, humans, and rain. The video is almost over now, so let's have a look at what we learned. You now understand how the datasets of the DCASE2018 Bird Audio Detection Challenge are structured, what kind of data they contain, and have an idea of what can be done with it. You also got a quick impression of how a typical audio classification system works and what kind of performance we can expect under unseen conditions with the available training data. That's it from me today. Have a great day.